where we focus on basic mechanical engineering design principles. But before we get on elements such as machine design, hydraulic machines, and thermodynamics, which will build up little by little towards it, I'd like us to first start with the basic engineering mathematics and physics that we will be using throughout this course. First of all, let's start off with position and displacements. Sorry there, choose a white pen, which is position and displacement. Now, some of you obviously would know what this chapter entails, and you could skip right through this video if you already know what these two aspects mean. But today I just want to focus on these and elements such as drawing the graphs P versus T, V versus T, and A versus T graphs. Now, what do I mean by position and displacement? Well, we could use these two instead of using distance. These two are directly related to distance, meaning that they are a substitute for distance. We can't use distance in physics because distance is in fact a scalar quantity. A scalar quantity, so we can't use it. Instead, we use its two cousins, which are both vector quantities. Now, these two, their magnitude is in fact a distance, but a distance with what? A direction. That's basically the only difference. Now, what do I mean by position? Position, I would define position as the depending firstly on the direction you choose. Depending on the direction you choose, can be positive or negative. Depending on those two, it would be defined as the distance from a fixed origin, or you could say a datum, basically. Yeah, you could call it a datum, basically. So depending on which direction you've chosen, it could be below or above. Let's say this is my datum, and then I throw a ball. This would be the position of the ball. This would be obviously it would be emitted. That would be the position of this ball with reference to your data. Okay, now that we've got that out of the way, let's take a look at an example. Okay, so now let's draw. Let's say you're throwing a ball here. You throw it upwards, it goes up and down in that kind of manner. Okay, so let's say this is your hand, and this is where you throw it from. Okay, and this is the direction of how it moves. That's how it will move. So what I'm saying is, say, let's take this side as positive, as upwards, and then downwards would be negative. Here is the top, and there's the bottom, as you can see. Now, in terms of position, let's say the ball is at the top. The ball here, its position would be positive 1.25 meters. See what I did there? I fixed the direction and its magnitude. And then here at the bottom, the ball's position, what would it be? It would be at 0. position, or we could say 0 meters. Yeah, it's 0 meters. So that's an easy, nice example for how to tell the difference between position and distance. Now, the notations we're going to be using, I just want to get this out of the way. So we got S, we got H, we got X, Y, and Z. These will be the position. We use these as our position, and they will be in meters SI units. We're using SI units, guys. So please do not forget that. And then T is for time, is for time in seconds, as you might already know. And then I'll use U and V uh, for velocities. Now we'll get to velocities in a minute, meters per second. And what I left is A, obviously is for acceleration. Acceleration is going to be meters per second squared. Okay, now we get to speed. Yeah, that's a really terrible stuff. So what is speed? So speed is also a scalar quantity. Scalar quantity. So we can't use, well, we can, but it's not really practical in most cases. Since it's a scalar quantity, we'll use its relative, which I would say its relative, which is velocity. And unlike its cousin, velocity, it has direction and magnitude. Now, I want you to remember something about velocity. Now, velocity, in fact, is a or is the rate at which at which what at which what at which this is changing. What do I mean by this? I mean that it's the rate at which the position is changing in meters, at which the position is changing. Now you can go back to mathematics and say, okay, it's actually the derivative of position, but we're not dealing with that now. We're dealing with in terms of physics, right? And of course, and of course, velocity will depend on sign convention. Okay, now we've also got that out of the way. I'd like to place an example for us to do to further understand this, which will require us to know how to draw and how to identify certain parameters in a position versus time graph. Okay, so without further ado, let's get to it. Okay, so I've written down the example here, as you can see. So let me read it out in case you can't read some of these words. So Amy has to post a letter on her way to college. The post box is 500 meters east of her house, and the college is 2.5 kilometers to the west. Now Amy cycles at a steady speed of 10 meters per second and takes 10 seconds at the post box to find the letter and post it. So she takes a bit of time at the post box. It takes 10 seconds from there. Okay, so now how might we draw this out? So let's start here. Let's say this is a line. Let's say this is a house. Let's call it H. And then this is the post box. Let's call it P because it's at the east. They did mention that it's at the east. And then let's say her college, which is at the west. Let me say, mark it with the C. Okay, she goes from her house. She travels eastwards. Then she goes back. Sorry for my squiggly line to college. Okay, so these are our main points. So from the house to the post is 500 meters. 500 meters. And from a house to the college, which is west, let me also draw a line here to match this up, is 2.5 kilometers to keep my units consistent. I'll say it's 2,500 meters. Okay. I think we got everything we want there. So they're asking us to draw a P versus T graph, which is a position versus time graph. Okay, so now how would we handle this? Well, we firstly have to remember what is velocity. Velocity, because it plays a really, really important crucial role here because we are told that it's a steady speed of 10 meters per second. It's a speed, it's not a velocity. We have to remember that velocity is, in fact, the rate of change, the rate of change of position. Because why? Because she's constantly changing her direction. So we want to know what's the rate of speed there, meaning that V is actually the distance, distance, oh, let me say total, divided by time, total, which also might be total. I don't know, depends on that instance, you see. So scenario number one, she travels 500 meters. We know the distance, but what do we want to know? Want to know how much time did she take? Well, we know that it's 500 meters. If you divide that by the speed, which is 10 meters per second, which is actually was given right here, it's 10 meters per second, we will get a speed, I mean, time of 50 seconds. Why? Because if we know that if we want time, we just have to divide into some math here and make time the subject of the formula. Then we will get time in seconds. And then scenario number two, she travels 0 meters in fact, because what is she doing? She is looking through the post box. She's taking her time there, and that time is 10 seconds. Scenario three, then now she goes to college, which is about what? 3,000 meters away. Now, what? You're probably asking yourself, why did I say? Because it strictly says here it's 2,500 kilometers, I mean, meters away from her house. Well, what did I say about displacement and position? The displacement is actually from the post to the college. So she actually traveled this 500 plus this 2,500 meters, meaning that in total she traveled 3,000 meters. Oh my gosh, that's quite a long time. So now it's 3,000 divided by the 10 meters per second because it's constant. She travels at that 10 meters per second constantly. She doesn't change it, which will give us a time of 300 seconds. Okay, now how do we draw that? How do we put that in graph terms? Okay, so now this is how your P versus T graph would show. You'd have to experience these would should be straight lines here. These lines should be straight. This one, this one means constant velocity. Then the one that's sloping down should also be constant. Now I want you to notice something here. There's actually a gap here. between here and here. That's 10-second gap. This that 10-second gap that she's waiting there in the post. Because if it wasn't there, then we were gonna start from here, then continue downwards. But because there's that delay of that 10 seconds, your graph should look like that. Then you could go on further and draw your what's this, v versus t, which is velocity versus time. How you would do that, I would give you a clue. You would use gradient. You'd use the gradient, and I would advise you to draw it directly under this graph. By drawing it directly under, okay, those are actually cool lines. You would draw it under this graph, making sure that this is your v and this is your t. Then using the gradients, you would end up with something like this. This one would represent 10 seconds, then it would be asymptote, and then this would be another time up to that 350. You see, and you would again would continue with your distance. I mean, yeah, with your distance versus time graph, which means the y-axis would be your distance, and this would be your time. And remember, distance is a scalar quantity, meaning that it would be constant. It wouldn't be changing, maybe. It would change a little bit here because what's happening, because there's a change, there's a little bit of change there because you drive from a house to the post, then back. You see, that's why you got a nice change, a little bit of skippy do there, then yep, there we go. It's going up, it's increasing. Yeah. Yeah, so that's basically how it happens for velocity and distance. That's their relationship. You could also use the relationship such as using the triangles to figure out the relationship between time, velocity, and position. But this is mostly the most common, most easiest way, and this is how we would use it in engineering, specifically mechanical. And later on, you would see why I do this in this way. So let's progress on to the next section. Now in this section, I'll be mainly focusing on average speed and velocity. Velocity. Sorry, average speed here. Now, what do I mean average speed? Now, Amy there, we did a lot of ideal work, I would say. Now, if we were to make it more a practical approach, which I would say realistic alternatives, realistic approach. I would say that Amy would start and stop instantaneously. I don't know if that's correct, but this is supposed to be instantaneously, okay? So how would we know the actual really speed that she did, that the velocity? Because remember, they said she traveled at a constant velocity of 10 meters per second. Well, we need to average it out. We'll have to know what's the average. You know, now in our terms, we would say the average would be given by the total distance she traveled over what? The total time, like I said earlier. But now pay close attention to the distance she traveled, which is that 3,000, or you could say 2,500. I mean, 2,500 plus 500 meters. And then total time traveled. Now I'm taking, which encompasses the 10 seconds plus the 50 seconds plus the 300 seconds, which would give us 9.72 meters per second. That's the actual speed that she's actually traveling. That's the instantaneous speed. That's the instantaneous speed that she's traveling. Okay, but what about the velocity? Because that's the speed. It's the speed. It's not the velocity. So what about the velocity? Okay, so to get the velocity, we would have to consider direction. You'd have to consider the direction, you know, and displacement. Displacement, not distance, displacement. So what do I mean? Now, let me place my average velocity formula here. So you can write it down there. It would be displacement divided by total time. Now, they did mention back in the story or in that section that the college is 2,500 meters to the west. So us taking east as positive, then that direction would be negative, meaning that now we'll have to divide by the total time to that 50 plus 10 plus 300, which will give us a negative 6.94 meters per second. So what's happening here? This is the 4 actually. Sorry for my terrible, terrible handwriting. That's actually supposed to be a 4. So what's actually happening? It means that if Amy chose to skip the post and go straight to college, she would take 6.94 meters per second to get there. To the west. Let me specify it and say to the west. That's the total time she would take, you know. Now that now that we've got that out of the way, um, on the next video, I'll be focusing on the ball example. Now, let's say we throw a ball into the air. What's the instantaneous velocity at any point you want to get? So please, guys, don't forget to like and subscribe. Thank you.